Hello ladies and gentlemen, my name is Janet Kelsey of Separation Science and I'd like to welcome you all to our latest webinar in collaboration with Thermo Fisher Scientific. Our topic today is a new integrated sample-to-result analytical workflow for the sensitive and reliable analysis of polar and ionic pesticides and metabolites. Let me introduce our presenters for today's webinar. Richard Fussell is a vertical marketing manager for the food and beverage market in the chromatography and mass spectrometry division at Thermo Fisher Scientific. He has more than 40 years of experience working in food safety analysis. Before joining Thermo Fisher Scientific, he worked as a senior scientist and advanced research fellow at the Food and Environment Research Agency in the UK, where he was responsible for the management and delivery of research and collaboration projects. Fausto Pigosso is the Director of Workflow Development, Food and Beverage in the Chromatography and Mass Spectrometry Division at Thermo Fisher Scientific. With over 25 years' experience in analytical chemistry and mass spectrometers, Fausto has contributed to the development of all GC and GCMS and ancillary devices offered today by Thermo Fisher Scientific. His analytical expertise in technology and applications is used for helping customers find solutions to their needs and challenges. And so, without further ado, I'll turn the presentation firstly over to Fausto. Fausto.
Thank you for the introduction. We want to take this opportunity to discuss the development, the capability and the benefits of the new product, Thermo Scientific Anionic Pesticide Explorer. This is a new sample to results analytical workflow composed of 4 modules. An extraction modules, as you can see on the slide, based on the European reference lab quick polar pesticides extraction method with solid phase extraction cleanup, followed by a high performance ion chromatography separation, which is the second modules, a triple quadruple mass spectrometer detection module, and a chameleon chromatography data system modules. The modules are fully integrated and validate to provide robust, sensitive, and reliable and multi-analyte determination of polar and ionic pesticides and metabolites at low concentration levels in a wide variety of sample types, as you will see later on in the presentations. This workflow is available as an off-the-shelf kit, which include all instruments, software, necessary consumables. We include also a suitability check standard solutions, method details, and detailed deployment guide for fast implementation immediately after the installation of the system. You will see in the presentation that the workflow provides results which are in compliance with the European maximum residual level regulation and European SANTE method validation guidelines, and is also highly productive and robust in routine analysis. So during the presentations, we will focus on background and analytical challenge for the analysis of polar and ionic pesticides. We will look at the existing analytical and target reporting limits for polar and ionic pesticides. We will review the features of each individual component of the analytical workflow, and we will discuss the optimization and benefits of the fully integrated ICM-SMS systems with electrolytic suppression of the eluent. We will then discuss the design and results of a validation experiments using wheat, leek, and baby food matrices. And this will include presentation of the results based on different calibration approach. And finally, we will give a short summary. Well, anionic pesticides are widely used in agricultural production residues and are often detected in food. For example, glyphosate is commonly detected in breakfast cereals, in beer, and more recently in honey. Etethone has been detected in grapes and pineapples, while, for instance, chlorate has been detected in fruits, dairy products, and baby food. So clearly, there is a need to improve methods for monitoring, but anionic polar pesticides provide a number of analytical challenges. As you can see on slide, they are small water-soluble molecules with poor chromatography retentions using reverse phase chromatography, so are usually not included in conventional multi-analyte LCMS methods. Consequently, monitoring of residuals of anionic pesticides in food is inadequate, allowing the potential for misuse to go undetected. European Food Safety Agency and European Commission has therefore requested the development of improved, more cost-effective methods to enable laboratories to generate more data and provide better controls. Among all challenges, European Food Safety Agencies have also indicated that residual definition of glyphosate analysis for risk assessment studies should be the sum of glyphosate and their relevant metabolites, normal acetyl glyphosate, AMPA, and normal acetyl AMPA, which would make the analysis even more challenging. Another issue is shown in these slides is the variation in the current maximum residual levels for the different commodities, most of which are set at the limit of determination, as shown in the table covering the three different matrices used for validation in this study, wheat, leek, and baby food. In most of the cases, laboratory, however, use a target reporting limit of 0.01 milligram per kilogram, so 10 ppb, even in cases where maximum residual levels are higher, as in the case of glyphosate in wheat. In addition, each stage of the analysis provides an analytical challenge. Simple extractions is performed with a modified version of the quick polar pesticides method. However, the method brings a high level of matrix co-extracted, and usually isotope label internal standard are used to correct for extraction efficiency. Very simple cleanup is performed to remove co-extracted. This is, however, very specific to the commodity and analyte to be removed. The lack of a generic cleanup makes the only strategy to be generally applied to all commodities just the dilution. It is also difficult to achieve sensitive, reproducible results using liquid chromatography with derivatization or through direct analysis using Illich or no suppressed ion chromatography. The polarity of this analysis does not allow direct analysis by reverse phase HPLC. Some Illich separation can suffer from metal contaminants that leach from using conventional metal-based ultra-high performance liquid chromatography systems. Some vendors, for instance, recommend flushing of the system with ADTA to minimize the interaction between analytes and metals. Ion chromatography with no electrolytic suppression is not robust enough, as detector cannot stand longer to the high ionic strength of the mobile phase. And this leaves as only options ion chromatograph with electrolytic suppression. Finally, triple quadruple is used as detector for targeted analysis, or in case of targeted or an untargeted analysis, use of high resolution accurate mass is an option. The final challenge is that all results must meet the European standard performance criteria. Let's have a look at the ion exchangers ion chromatography and the basis of the anionic pesticide explorer. The left side of these diagrams represent the mechanism of separation achieved with an ion exchange on the stationary phase particles. Usually the competitive polarity between target analytes and mobile phase toward the active site on the stationary phase generates the delay of target analytes and the chromatography separation. In ion chromatography, the typical eluent or mobile phase is potassium hydroxide, just increasing the eluent concentrations and it's possible to push the analyte ions and get the separation completed. Of course, potassium hydroxide is not compatible with mass spectrometer detector, but using a suppression technology, a big innovation from Dionex, it is possible to convert highly caustic mobile phase to pure water and the potassium salt of the analyte to the acid of the analyte. In this way, we are able to connect the IC to the mass spectrometer without worrying about the high concentration of salts. Additional, this enables the use of high-capacity IC columns that enable higher sensitivity, higher capacity versus food co-extractive interference, and excellent selectivity. The other advantages of the Dionex ion chromatography systems are related to the inertness of the systems achieved using peak and no metals along all analyte pathway. The metal-free IC systems eliminates the issue of chelation of polar analytes by metals ions leaching from the LC systems, while the reagent-free electrolytic eluent generation removes the tedious preparation of the mobile phase. Another advantage of generating gradients in situ using the eluent generator cartridge is that the gradients are extremely reproducible so that retention times are really stable. And we spoke already about the advantages of using electrolytic regeneration suppressor for the connections to the mass spectrometer. The triple quadruple used in all these experiments was the TSQ Altis. Of course, there is a lot of new technology in this triple quadruple, and you can see some highlights on the schematic on the right-hand side of the slide. Innovation in the ion source, mass analyzer, RF electronics offer high sensitivity, reduced noise, and more data points with high SRM rates. You can confidently quantify compounds at extremely low concentration in the most challenging matrices, like, for instance, food matrices. The systems offer very high sensitivity in negative mode that is crucial to reach low level of concentration for anionic pesticides. All technical enhancements, such as novel ion optics, able to reduce chemical background by ion beamer blocking, and source design, increase robustness, reduce maintenance, and improve reproducibility. Chromeleon software was used to acquire, process, and report data. Among all key features, it provides the ultimate confidence of the highest data integrity and compliance-ready data processing. Compliance tools are available in the result panels and dynamically updated during the data acquisition for easy and immediate checking of results, so saving time. The screen on the right-hand side shows, for instance, for selected analyte, in this case perchlorate, quantitation and confirmation ions, linearity, and ion ratio deviation, using a color-coded flag to visually highlight compliance, non-compliance throughout the sequence. So if we are looking at the full system configuration, it includes a Dionex Integrion high-performance IC system fitted with an electrolytic eluent generator and conductivity cell, coupled with an autosampler and TSQ Quantis triple quadruple mass spectrometer. Separation is achieved using an ion pack, 19 GAR columns and analytical columns, with elution of polar anionic analytes using potassium hydroxide gradients. An ionic dynamically regenerated suppressor installed after the columns convert potassium hydroxide to water before eluent flow enter conductivity detector and mass spectrometer, which are connected in series. There is an auxiliary pump adding acetonitrile modifier to, let's say, improve the dissolvations into the MS source, and typically increasing response for most of the analyzed by 3 or 4 times. And as mentioned, the system control data acquisition, data processing is done using the Chromeleon chromatography data systems. The method has been developed with representative commodities: wheat flour as an example of dry commodity, leek for high pigment content, and baby food, fruit-based, as an example of a challenging matrices. All validation has been done using European Sante regulatory guidelines. The method consolidated determination of polar and ionic pesticides into single analysis, increasing, of course, productivity and reducing cost. The workflow, as mentioned, is provided with a system suitability check standards to assess performance during installations. The software includes a preloaded acquisition method, data processing, and reporting templates. For instance, if we talk about triple quad MS, all SRM transitions are optimized and preloaded into the software with relative collision energy and other MS parameters. The system also includes a detailed operating manual. We call it deployment guide for fast implementation and enablement of ongoing optimum performance. The development of the method started with the optimization of the MS parameters and started in identifying the optimum condition of the electrospray ion source. All parameters were optimized for each individual analyte. We evaluated signal stability, robustness of the system, and maximum response. And the final setting are a compromise between maximum response and signal stability. The next optimization involved optimizing all SRM transitions, infusing spike standard into the system, and generating multiple transitions for quantify and qualify ions for each pesticide, and then selecting those ions that providing the optimum peak, free from interferences or high background level. All those SRM with relevant MS parameters are saved in the compound database preloaded into the software. And with that, I handed over to my colleagues, Richard Fassnell, to show you all the results of this validation. Please, Richard.
Yes, thank you, Fausto, for your comprehensive description of the workflow components. So, as you said, let's move on to the validation experiments and the results. So, we started the development of an extraction method using wheat flour because it is a dry commodity with a high concentration of matrix co-extractives. We hoped that if the method was successful for wheat, the same method would be applicable to other matrices. The extraction method is a modification of the CUPE, or quick polar pesticides extraction method, developed by the European Reference Laboratory for Single Residue Methods. So firstly, 5 grams of wheat sample is rehydrated with 10 mils of deionized water. The aqueous slurry is extracted with methanol, and then the mixture is cooled at -20 for 15 minutes prior to centrifugation. The supernatant is then diluted tenfold with water before solid phase extraction cleanup and filtration using an on-guard reverse phase cartridge connected to a 0.2 micron filter. The on-guard SPE removes the fine precipitate that is formed in highly aqueous extracts of wheat and also makes it easier to filter the extract. The filtrate is collected in polypropylene vials ready for injection, which is in this case 25 microliter. For the calculation of recovery or for preparation of procedural standard calibrations, the native compounds and or isotopically labeled internal standards, if available, were spiked onto the sample before extraction. but for the preparation of matrix match calibration standards, the analytes were spiked after the cleanup as shown in the schematic. The total ion chromatogram of a standard in the top right section of this slide shows the chromatographic separation of the analytes and also highlights the difference in the mass spectrometry response of the different pesticides, which are all at the same concentration. The insets show the extracted ion chromatograms for the quantification and qualifier ions for each individual compound at 0.01 milligram per kilogram or 10 ppb in wheat flour. Just note the excellent response and peak shape for N-acetyl glyphosate, a compound which is difficult by helix separations and subsequently sometimes missing from literature publications. This slide shows the same information for the other compounds included in the same chromatographic run. We also need to mention the fact that the retention times are extremely stable. In calibration plots, the response for 12 compounds are all linear over the range equivalent to 4 to 200 nanograms per gram with satisfactory R-squared values. The experiments in this presentation were carried out at our Customer Solution Center in Beijing, China, where they were not able to import the isotopically labeled internal standards for all of the anionic pesticides of interest. Therefore, different calibration approaches were evaluated in an attempt to compensate for recovery losses, and this table shows the results obtained. So, using matrix match standards, IEE, that is, prepared after extraction and cleanup with no internal standards, then AMPA, N-acetyl glyphosate, and glyphosate produced relatively low absolute recoveries, as highlighted with the purple. And this is possibly because of binding of these particular analytes to the matrix. Having said that, the results could be considered sufficiently reproducible for the purposes of screening analyses. Now, spiking the samples with labeled standards before extraction and then using matrix-matched calibration with labeled standards, the results are corrected very nicely, as shown in the columns highlighted in the pale amber color. But of course, only for the compounds for which we have the internal standards available. And then finally, using procedural standards, which is a calibration series prepared by spiking before extraction, apparent recoveries are corrected for losses as highlighted in the pale green. Now, this apparently worked very well, but a word of caution that this is only validation using a single sample matrix. When we evaluated a number of different samples rather than just one individual sample, the results were more variable. Even if we use the same sample for exact matrix match spiking and calibration, as was the case in this table, and this means that results for sample 1 is based on spiking and calibration using the same sample, number 1. The result for sample 2 is based on the spiking and calibration using the same sample, number 2, and so on, which is the best scenario. And then other experiments also confirmed that the variation between samples is too high to allow the use of matrix match calibration or procedural standards prepared from one sample to accurately calculate incurred residues in different samples. So therefore, in the analyses of wheat, the use of labeled standards or standard addition seems to be the only way to ensure accurate measurement of incurred residues extracted. Of course, this does not take into account any issues with the actual extraction efficiency. Another issue encountered in our experiments was the fact that the residues of glyphosate and phosphonic acid appeared in the samples purchased, which further emphasizes the need for increased monitoring. This slide simply shows the quantification and identification of chlorate at the EU maximum residue level. The results for chlorate and all other compounds except those with high values in the blanks are fully compliant with the latest SANTE guideline criteria for method validation. Another important consideration in routine analyses is robustness. Here, this shows that after 80 consecutive injections of wheat flour extracts, the ion source remained clean, and the peak shapes, retention times, and detector responses remained very stable. Leek, a vegetable crop, proved to be a much easier matrix compared to wheat and gave good data irrespective of the calibration approach. Using procedural calibration standards, all recoveries were in the range 70 to 120% and all RSDs were below 10%. By contrast, baby foods purchased in China proved to be a very challenging matrix. So much so, we needed to modify the SPE cleanup step and inject 50 microliters instead of 25 microliters. We also used Hypercept PGC instead of on-guard reverse phase SPE. And the reason was that Hypercept eliminated the increase in system pressure that occurred on injection of non-cleaned up or on-guard cleaned up extracts of baby foods. It has been suggested that this could be due to thickening agents used during the manufacture of baby foods. Also, on this slide, you can see the elution profile of AMPA glyphosate and N-acetyl glyphosate from the Hypercept cartridge, which has proved to be very effective with minimal losses of analytes. This table shows the results using the conventional approach to validation, testing a single sample matrix at 3 different concentrations. All of the results are in compliance with the SANTE criteria, except chlorate and perchlorate at 2.5 nanogram per gram and phosphonic acid at 10 nanogram per gram, and only because of residues in the blank. Now this slide shows the results for anionic pesticides spiked at 5 nanogram per gram in 9 different baby foods using the Hypercept cleanup method, but with no labeled standards. The calibration was using exact matrix matched standards, indicating minimal losses of analytes during the cleanup. And most importantly, the SPE cleanup increases workflow robustness and minimizes system downtime. During method development, the Dynex IC guard and analytical column set has been used for 1,500 injections, including more than 1,200 injections of baby food, while the ADRS suppressor has been subjected to over 700 injections of baby food and wheat flour extracts cleaned up by SPE. The next 3 slides show the extracted ion chromatograms for anionic pesticides at low concentrations in a baby food matrix. Firstly, glyphosate and metabolites. This shows the extracted ion chromatograms at 5 nanogram per gram, and also the LOQ limit of quantification at 2.5 nanogram per gram. And now glufosinate and metabolites, and for the other analytes as well. The ion ratios were within the expected range compared to the standards for all of the analytes shown on all 3 slides. And here we have an example of an incurred residues detected in baby foods. Perchlorate in the blank sample at 0.7 ppb and phosphonic acid at 20.3 ppb, so a much higher concentration. And another example of a baby food which contained perchlorate, phosphonic acid, and chlorate, all in the same sample. So we have provided a lot of information. So what does it all mean now and into the future? We believe that we can meet the current EU maximum residue levels and residue definitions as well as the Sante method validation criteria for all matrix analyte combinations tested. Furthermore, we are much closer to be able to meet the EU residue definition for glyphosate should the residue definition change in the future. The ion chromatography mass spectrometry approach is also being used successfully in commercial laboratories. For example, Now Foods presented a poster at AOAC 2018 which documented the analysis of glyphosate, AMPA, glufosinate, and MPPA in botanical samples such as maca, silymarin, and cat's claw. Limits of quantification were well below 10 nanogram per gram, and the system is performing well after almost 1 year. Now Foods compared HILIC with IC and found that the ion chromatography provided lower detection limits, which was an important factor for monitoring their raw ingredients. So in summary, the IC MSMS anionic pesticides analytical workflow can provide compliance with current EU MRL residue definitions levels and EU Sante guidelines for method validation and ongoing quality control, as demonstrated for leek, wheat, and baby food matrices. It can also provide higher productivity by aggregation of 2 to 3 methods into a single analysis and long-term robustness, proven by analyses of a large number of samples of complex matrices such as wheat and baby food. And just a reminder that the new Thermo Fisher Scientific Anionic Pesticide Explorer is available as an off-the-shelf analytical workflow, including preloaded acquisition and data processing methods and system suitability check standard solution. All of the instrument and software parameters have been optimized and documented to assist the installer with fast implementation and for the operator to routinely maintain high system performance and especially sensitivity. Also, the standardized configuration will enable Thermo Fisher Scientific field specialists to provide improved customer support. Fausto and myself would like to take this opportunity to acknowledge our colleagues at the Beijing Customer Solution Center for their support in this project, especially Shilei Guo and Ying-Chen Li. And finally, thank you for taking your valuable time to join us today. We invite you to stay connected with us, and if you want more information on this topic and are interested in other analytical workflows and resources, then please take a look at our Food and Beverage Analyses website. I will now hand you back for questions. Thank you.
Well, thank you both for that excellent presentation. We now have time for your questions received via the Q&A box. And our first question is for Richard. Have you tried using standard in solvent with IS so you don't need matrix blank?
Yes, thank you for the question. Yes, we include a solvent standard in order to check the ion ratios for the purpose of identification, but we do not use a solvent standard for quantification purposes because of the matrix suppression effects, which means that we will not get the correct answer.
Thank you, Richard. And the next question again for you, Richard. Is it possible to use the IC method for trace analysis of polar organic acids like trifluoric acetic acid?
Yes. We haven't tried to analyze those compounds alongside of the ones which we discussed today under these conditions, but yes, it's possible. You may have to change the conditions slightly.
Okay, thank you very much. And the next question is, what weight was used for leek and how much water was added?
The amount was 10 grams. And the amount of water added was as specified in the CUBE EURL method, which, if I remember correctly, is about 0.9 mil.
Excellent. Thank you, Richard. The next question again for you, Richard. You covered the analysis of anionic pesticides, but can you use the same system for cationic pesticides?
This is for me, Janet. Anyway, this is Fausto. Yeah, the hardware and the software that we presented today can also be used for cationic pesticides. There was another question on the same topic, which can be, let's say, covered here regarding doing using these systems to analyze diquat and paraquat. Of course, we need to change the eluent cartridge. We need to change the column to a cationic exchanger and the suppressor. Of course, it is possible to use a single-channel system, but it will take something in the range of 1.5 to 2 hours to change and equilibrate the system. But there is also a two-channel system available. It's called Dionex ICS 6000s. That can be set up with one channel for cations and the other for anions. So then operator can then switch from one to the other in minutes.
Okay, thanks, Fausto. And this next question is for Richard. You gave some numbers of injections on the column, but is there any other evidence to show the robustness of ion chromatography columns?
Yeah, this is a very important point. So the Dionex anion exchange resin technology has been developed over more than 40 years, and the column robustness is proven in many laboratories analyzing a very diverse range of matrices. If you remember, during the presentation, I mentioned that we injected more than 1,500 wheat and baby food samples on the same guard column and analytical column. And I can update you and say that this column system is still producing very good results. So it's now many more than 1,500. And also I can add that from my own personal experience before I joined Thermo Fisher, I used to work in a laboratory where we used a lot of ion chromatography, and we used to inject a lot of samples of large volumes, and we used to clean the columns up with very aggressive cleanups using acids, etc. And the columns proved to be extremely robust. So hopefully that's will be sufficient to give you confidence of the robustness of the columns.
Okay, thank you, Richard. And the next question for Fausto. I need to analyze polar pesticides, but only a low number of samples. So I would like to know what other applications are also possible by ICMS.
Thank you. Yeah, if a compound is of an ionic nature, then it should be able to be analyzed with the ion chromatograph systems, and the ICMS is very versatile systems. So in terms of compounds, of course, quite a large range of anions can be analyzed by the systems, chloride, nitrate, nitrite, phosphates, sulfates in water. In terms of matrices, just to quote some of them, nitrates and nitrates in meat products and vegetables, organic acids, especially oxalic acid in honey, acid contaminants in food packaging, just to mention a few others, bromate in bread, acetic acid in environmental samples, speciation of metals, but of course we will need to have an ICP-MS and many more.
Okay, thank you, Fausto. And another question for Richard. What routine maintenance is typically required for an IC system?
Yeah, okay, thank you for the question again. The system contains an electrolytic eluent generator, which means that you only have to add water and the cartridge which contains potassium ions will be calibrated to produce the gradient. So all you need to do in this case is to change the water on a regular basis. So we would recommend that you exchange all of the water after 2 days of use. Simply, we don't top up the water, because if you keep topping up the water, then that gives an opportunity for microbial growth, which will contaminate the system. Other things we do is we monitor the performance of the electrolytic suppressor which is placed after the column in the software. And from the data that you get back, you can get an indication of when it's necessary to clean the suppressor. It's very straightforward to do. It just takes a few minutes. And you can decide whether you want to just flush it with water, or whether it's necessary to use a very weak acid, but we can provide advice on that. And you should do it at least once a month anyway in order to rehydrate the suppressor in order to get the optimum performance. Other things we do, inject a small volume of organic solvent, for example 2 microliter of acetonitrile, occasionally into the system to just make sure you clean the tubing, and also helps to clean the column as well. Other things, perhaps not a maintenance item, but a tip really, is that if when you're doing analysis of matrix, it's good to check in advance that matrix will not crash out of solution in 100% aqueous phase, because sometimes that can cause issues with blocking. But having said that, if you use the reverse phase cartridge which we described in the experiment, that provides protection against that possibility. So those are just a few things which we can do. We can also clean the column as well if necessary, and it's a really simple maintenance. Ongoing regular maintenance will give you very good performance over an extended period of time.
Well, thank you, Richard, and perhaps you can answer this next question. Have you evaluated any online cleanup options?
Yeah, well, this is a really great question. The simple answer is no, not in the case of this particular application. But since you already have the availability of switching valves, it should be possible, especially if you are interested in may be a limited number of analytes in a particular matrix. So one of the problems is with perhaps if you want to do inline anion exchange trapping or concentration, then it's quite difficult to set the conditions to trap all of the analytes which we described in today in this presentation. But perhaps an option that we should consider is that we could almost automate like an on-guard type system where we have a pass-through column, and then we can back flush it in line. We can flush the analytes onto the column. And there was a publication back in the early 2000s where somebody, like a researcher, actually used to take this approach, but then it was only for one compound. So I think it's not available at the moment, but something which hopefully that we may look into in the future.
Okay, thank you, Richard. And the final question for you, Fausto. How robust is the electrolytic suppressor device?
Yeah, as Richard mentioned earlier, and as you have seen in the presentation deck, within the anionic pesticide explorer workflow, if the suppressor is connected using the right the correct tubing, the right size of the tubing, as Richard mentioned, we can monitor the back pressure and the voltage, and of course, if the suppressor is cleaned up occasionally, it should last for many injections. Of course, this depends all on the matrix and cleanup procedure, but more than thousands matrix injections. Richard already mentioned some of the tips, but another one is to, of course, use an on-guard SP cleanup to protect the whole system for the matrix interference to affect the suppressor capability. So that's a few tips for ensuring a suppressor will last thousands of injections.
Well, thank you again, and if any other questions do come in, I'm sure that either Richard or Fausto will be happy to respond to them via email. Thank you also to our scientific partners in this webinar, Thermo Fisher Scientific. And finally, I would just like to remind everyone that a recording of this webinar will be available soon, and you will all be sent a link to this. And with that, I'd like to thank you all for logging in and listening. Thank you and goodbye.